In this video, I'm going to look at entanglement in Bohmian mechanics, and in particular, the entanglement of spin states. So this is this is looking at the same paper that I was looking at in the previous video. So this is just the continuation of the previous video. And so remember that in Bohmian mechanics, we just have the Schrodinger equation and we have the guiding equation, which are the two things that dictate the motion of our particles. And so in these last several videos, I've been looking at these two papers by Travis Norson. So I looked at the pilot wave perspective on scattering and tunneling. And in the previous video and this video, we're looking at the pilot wave perspective on spin. And so as I've been stressing here with these two papers that I've been looking at, what these are doing is trying to show that Bohmian mechanics can come up with these same predictions as standard textbook quantum mechanics. And that's because being able to do this is a necessary but not sufficient condition for a candidate interpretation of quantum mechanics to be plausible. And that's because, as I've been stressing, the predictions of textbook quantum mechanics are extremely successful. They make very good predictions that experiments time after time show to be correct. They are obviously probabilistic predictions, but they are predictions that are borne out in experiments. And so if you have a interpretation of quantum mechanics that does not at the very least recapitulate these same predictions, then your candidate is not a very good one, and so it probably ought to be rejected. And so remember, in textbook quantum mechanics, we have entanglement here where no matter how far apart these particles are, if you make a measurement on one, you know immediately, instantaneously, what the outcome of a measurement on the other one would be. And so this is non-locality because it doesn't matter how far apart these experiments are being performed. You know immediately, not at the speed of light, but immediately what the measurement on the other particle would be. So if we have Alice here making a measurement on her particle, then she would immediately know that if Bob did a measurement down here, what the result of his measurement would be. And so this is something that is predicted from textbook quantum mechanics. If you want to know more about that, I would recommend checking out my quantum mechanics playlist where I go through the Griffiths textbook and show all the calculations and things like that and how that comes about. But this is a prediction of quantum mechanics, and experiments show that it is in fact true. And so we need for our Bohmian mechanics to be a candidate theory or interpretation of quantum mechanics, it needs to be able to explain how this occurs. And so that's what this is going to be doing. And so again, I have some text colored here, and that's what I'm going to follow. The first part of this is just talking about the contextuality of entanglement here, and it's just, or of spin rather, and it's just say that if we have this, so this was the first figure in this paper, where it's just showing that this is in a superposition, the particle goes through here, and then it could either follow the wave going up or down, depending on where the particle was in this wave. Within the z direction. So if it was at the top of this wave, it would go up. If it was near the bottom, it would go down. And then he says that, so we see here we have the south pole of our magnet on top and the north on bottom. He says that if we put the north on top and south on bottom, we would still get the same splitting, but now we would just count up as the thing going down. So that's why we have the plus here, we're up here, the plus up in the upper beam there, and then the negative is in the upper beam right here. And so it's just talking about how this is contextual based on the type of apparatus we have, whether we put the north and south on the top and bottom or on the bottom and top right here. And so He says, for this case, the particle velocity in the overlap region is proportional to y, i.e. the particle trajectories simply continue in a straight line all the way through the overlap region till they finally emerge into one of the now spatially separated subbeams corresponding to their initial lateral positions, so their positions in the z direction, as I was saying, within the incident packet. That part is identical whether we use the original, so this is the Stern-Gerlach Z here, or instead the alternative Stern-Gerlach prime Z here, which is what he's calling this setup right here. This is the prime setup. This is the original setup. But there is a crucial difference between the two devices. If, say, the particle happens to start in the upper half of the incident packet, it is destined eventually to find itself in the upward deflected subbeam and hence be counted as spin up along Z. If the measurement is carried out using the Stern-Gerlach device, so the original Stern-Gerlach device. But if instead the measurement is carried out using the primed device, the exact same particle, that is the exact same wave function, exact same particle location in the upper half of the wave packet, is instead destined to eventually find itself in the upward deflected subbeam and hence be counted as spin down along Z. In short, for the deterministic hidden variable pilot wave theory, the outcome of measuring the z component of the spin particle is not simply a function of the initial state of the particle, i.e. the particle plus wave complex. The exact same initial state can yield either of the two possible measurement outcomes, depending on which of the two possible experimental devices is chosen for performing the experiment. And so he's contrasting this to what he says in the beginning here what he calls naive hidden variable theories, which would say that there is some definite spin on the particle. And so what that would predict then is that if we put the particle through a Stern-Gerlach device that look like this and say it has a definite spin up, then it's going to go up this way. Whereas here, if it has spin up, then it might end up still in this upper part of the beam. Whereas he's saying that in the Bohmian mechanics, this is not a naive sort of hidden variable theory. And so we still do have this contextuality, which the Kochen-Specker theorem, as I discussed in a previous video, tells us that any theory of quantum mechanics must have. And so he goes on to say, this is a concrete illustration of the fact that is usually put as follows. For the pilot wave theory, spin is contextual, that is the outcome of a measurement of a certain component of a particle's spin depends in the pilot wave theory not just on the initial state of the particle, but also on the overall experimental context, i.e. on the particular way that the measurement is implemented. And so down here, it says more generally, non-contextuality can be understood as the requirement that each observable should possess a particular definite value that will be revealed by a measurement of that observable, no matter what compatible observables are perhaps being measured simultaneously. Whereas we see in the Stern-Gerlach experiment, the other thing that we're measuring here is the position of the particle. So we're measuring the spin of the particle by measuring the position of the particle. So we're looking at this as the position in the z direction here. And so that is our compatible other observable there. And so he's saying that non-contextuality would tell us that our observable should possess a particular definite value and will be revealed by a measurement of the observable no matter what compatible observables are perhaps being measured simultaneously. And so that's what I was saying before about how if we're looking at naive sort of hidden variable theory, then whether we are measuring, so the spin up here in this case has the particle going upward, and then in naive hidden variable theory, even if we flip these magnets, we would have the spin up being going in the upward direction here because the up and down in the z direction is the compatible observable that we are simultaneously measuring. So he continues, for our purposes, the upshot of all this is the following. In the literature on hidden variables, one often finds the implication that the requirement of non-contextuality is quite reasonable in the sense that contextuality would supposedly involve putting in by hand an obviously implausible ad hoc kind of apparatus dependence. But as the simple example of the contextuality of the pilot wave theory involving the Stern-Gerlach and our prime Stern-Gerlach based on measurement of z-spin makes clear, this is not the case at all. The context dependence arises in a perfectly straightforward and natural way, again, as a direct consequence of the fundamental dynamical postulates of the theory, the Schrodinger equation and the guiding equation. And so this is showing that this contextuality that our Koch-Specker theorem tells us must be true of any theory of quantum mechanics is true in Bohmian mechanics. Bell's 1966 paper closes by noting that Bohm's 1952 pilot wave theory eludes the various no hidden variables theorems by means of its contextuality, but that the context dependence implies a non-local action at a distance in situations involving entangled but spatially separated particles. And so what he's saying here is that the entanglement that we're going to be talking about here in a minute actually comes from this contextuality of quantum mechanics that must be the case given the Koch-Specker theorem. So, quoting Bell here, he says, in this theory, the Bohmian mechanics, an explicit causal mechanism exists whereby the disposition of one piece of apparatus affects the results obtained with a distant piece. Let us explore this type of situation in which the pilot wave theory's contextuality implies a non-local dependence on a remote context. So consider a pair of spin half particles propagating in opposite directions along and already widely separated along the y-axis. So again, we're looking at entanglement, so we want to say that these two experiments are happening very far away from each other. The initial spatial part of the two-particle wave function can taken to be this. So this is our wave function right here, where this would be one of the particles at position x2, and this would be the other particle at position x1. So we're saying x2 is in the negative d direction, and the particle 1 is in the positive d direction. So this represents a plane wave packet centered here in the d direction with a central vector which is going in the y direction. So consider first the case in which the spin part of the initial state also factorizes, which means that we can sort of separate these two things out here, meaning that they are not entangled with each other. So that the total state can be written like this. We may introduce the so-called conditional wave function, which I discussed in a previous video for particle 1 as follows. So we're just getting the wave function for particle 1, sort of holding the position of particle 2 in this position right here. So we're evaluating it with particle 2 at this actual position here. So as I said in a previous video, we call it the conditional wave function because we're essentially saying the wave function of particle 1 given that particle 2 is in this position right here. Where this x sub 2 here is, of course, the actual position of particle 2. The conditional wave function for particle 2 would be defined in a parallel way. So we just do this for particle 2, but with particle 1 being in an actual position there. These conditional wave functions are convenient because the dynamical law for the particle positions, the guiding equation, can be reformulated to give for each particle an expression of the particle velocity in terms of its own conditional wave function. So he's just saying in general we can do this conditional wave function for sort of any number of particles that we want. So the conditional wave functions can thus be thought of as one particle wave functions, each of which guides its corresponding particle. So I'm going to skip ahead a little bit here. And again, this is going to be linked to in the description down below if you want to read through all of this. And everything that I'm reading through here is mostly verbatim from the paper from which I'm taking this from, so you can read the paper in its entirety, which will be linked to in the references part of these lecture notes. And so if you want to read all of this stuff on your own, then you can do that. I'm sort of skipping to the highlights here, uh, just to at least try to make this video, not be like an hour and a half long. But anyway, so continuing on. So if, however, the spins of the two particles are initially entangled, so what we were talking about up here where he says that we can factorize them, is that these are unentangled particles. So if these are entangled, then we get this, where we see we cannot factorize this. We separate these things out in any way so that we get something where we have the two particles having their own wave functions that are just sort of products, where the total wave function is just a product of the two. So this is unfactorizable, and so we have here that these particles are entangled. And so we're going to be looking at something like this from figure 6. So this is an illustration of the two scenarios that are going to be discussed. In the top frame, particle 1, which is on the right side here, encounters its Stern-Gerlach in the z-direction device. The particle is found to be spin up, so it's definitely going in the spin up direction, so that's what these solid lines are here. If particle 1 goes up, the collapse suffered by the conditional wave function of particle 2 on the left causes it to go down, so these solid trajectories, regardless of its initial z coordinate. So it's saying that we are measuring particle 1 and it's going up, so we know that particle 1 was in the upper part of this wave function in order to go up. But it's saying that because of this collapsed conditional wave function, even if particle 2 is in the upper part here, it now must go down. So we see all of the world lines here lead to going down for particle 2. And so again, regardless of its initial z coordinate. So on the other hand, if particle 1 goes down, the collapse causes particle 2 to go up instead, regardless of its initial z coordinate. In the lower frame, particle 1 is not subjected to any measurement. So now we're looking at this one right here. So the particle just keeps going to the right. So the result of measuring the z spin of particle 2 is then determined by the initial z coordinate of particle 2. The difference between the two scenarios exemplifies the contextuality of the pilot wave theory, since the result of measuring the spin of particle 2 depends not only on the initial state, but on whether or not the spin of particle 1 is measured jointly, and also on its non-locality, since the choice of whether or not to measure particle 1 could be made at space-like relativistic separation from the measurement of particle 2. And so it's just saying that if we don't measure particle 1, then particle 2 could go either up or down. But if we do measure particle 1 and it happens to go up, then particle 2 must go down. And conversely, if particle 2 or particle 1 rather happen to go down, then particle 2 must go up. And so we'll read through this in the text here. So suppose, for example, that both particles are to be subjected to a Stern-Gerlach device in the z direction, so an SGZ-based measurement of their z spins. And suppose that particle 1 encounters this SGZ device first. A simple calculation shows that in the overlap region behind the magnets, so that's this triangular part here. So if we put a line going down right here, we have this triangular part here, that's the overlap region. So in the overlap region behind the magnets, the velocity of particle 1 will be proportional to y. It will simply continue in a straight horizontal line through the overlap region. It will then exit the overlap region into one or the other of the two downstream sub-beams. So that is these beams right here, that where they are fully split from each other. And that depends on its initial z coordinate. If the particle happens to have started in the upper half of the packet, it will end up deflecting up and being counted as spin up, whereas if it happened to have started in the lower half, it will be deflected down and counted as spin down. Supposing for notational simplicity that the two now spatially separated subbeams are bent, say by an additional appropriate SG sort of Stern-Gerlach type magnet, so that they again propagate in the plus y direction, but with displacements plus or minus delta in the z direction. So it's essentially say that we have some other Stern-Gerlach device right here that causes it to even out so that it's now going completely horizontal in the y direction. Uh, and it's displaced in the z direction by some amount delta here. So it would be displaced, say it's following this top line here, it goes up, and then it gets bent back into the completely horizontal. So there's some difference between the line here and this line here, and that is our delta. The two-particle wave function after particle 1 has passed through its Stern-Gerlach device will take this form here. So this big, long, complicated looking thing where we see that we have these entangled spin states here from the chi plus z on particle 1 and minus z on particle 2, or minus z on particle 1 and plus z on particle 2, which is just telling us again that if particle 1 is going up, then particle 2 has to be going down and vice versa. So that is the overall wave function is a superposition of the two terms, one proportional to particle 1 up, particle 2 down, and the other proportional to particle 1 down and particle 2 up. So the actual location of particle 1 will be either the z equals delta or negative delta, again depending on its random initial position. It is thus meaningful already at this stage to speak of the actual outcome of the Stern-Gerlach based measurement in the z spin of particle 1. The crucial point is now that the conditional wave function for particle 2, the thing that will determine how particle 2 behaves when it subsequently encounters its Stern-Gerlach device, depends on where particle 1 ended up. If particle 1 went up, that is if the position here is now in the support of this, so we see this is in this d prime, the delta direction, then the conditional wave function of particle 2 is proportional to this right here, and its subsequent interaction with the Stern-Gerlach device will, independent of the exact position of 2, result in a deflection down. And so again, this is all just a long-winded way of saying what I already did, which is that even if this particle 1 happens to go up, no matter where in the wave packet particle 2 is, even if it's at the top, it's going to go downward. Whereas if instead of particle 1 ended up going down, then particle 2 would go up. That is, the conditional wave function of particle 2 collapses as a result of the measurement on particle 1 to a state of definite z-spin. This happens, however, despite the fact that the two-particle wave function obeys the unitary Schrödinger equation without exception. And what he means by that is that there's no collapse in the way that we think of in textbook quantum theory, where the Schrödinger equation, where the particle sort of stops obeying the Schrödinger equation during a measurement. That's what the collapse in textbook quantum theory tells us, is that the particle obeys the Schrödinger equation at all times except during this weird thing that we call a measurement. It suddenly collapses and is no longer obeying the Schrödinger equation. Whereas in Bohmian mechanics, he's saying that the particle is always obeying the Schrödinger equation. And so that is without exception. And the usual quantum mechanical statistics are reproduced. So again, that's the thing that he's trying to show here, is that Bohmian mechanics can reproduce these quantum mechanical statistical predictions. The two possible joint outcomes, so particle 1 spin up and 2 down, or particle 1 down and 2 up, occur with 50% probability. Of course, the pilot wave theory being, after all, deterministic, these probabilities are quite reducible. In particular, which of the two joint outcomes occurs depends on the quantum equilibrium hypothesis, which, remember, means that our particles start in a position that is going to be proportional to the wave function psi squared. So the outcomes occur depends on the random initial positions of particle 1, and specifically its random initial position in the z coordinate. So whether the particle 1 is in the upper part or the lower part of our wave packet. In order to make the non-local character of the theory absolutely clear, it is helpful to now consider an alternative scenario in which particle 1 is not subjected to any measurement. So again, this is just kind of the long-winded way of talking about what we're looking at in this lower panel of figure 6 here. And so, for example, perhaps Alice, who is stationed there next to particle 1, decides at the last possible second before particle 1 arrives. And so the reason he makes this stipulation here is because of something that I'm going to talk about in a later video, and that has to do with what's called parameter independence. And so, as I discussed in one of the earlier videos in this Foundations of Quantum Mechanics playlist, is this idea that two events that share an event in the same light cone cannot be said to be sort of completely independent of each other. And so what we want when we get to the Bell inequality is that our two events can be said to be completely independent of each other. And so this is why it has to be that this happens at the last possible second before particle 1 arrives. It can't be something that was decided at the beginning of the experiment, say. It has to be something that comes at the last possible second so that we can maintain what is called parameter independence. But I won't get into that at this point. So again, Alice is stationed next to it and decides at the last possible second to yank the SGZ device out of the way so that we end up not measuring particle 1. So again, that's what we're looking at up here where we're not measuring particle 1. But then particle 2 will behave in just exactly the way we previously described for particle 1. So it could have a 50% chance of going up or down based on its position in the wave packet. The non-locality is thus clear. Even for the same initial state, two-particle wave function given by equation 38, where equation 38 was this right here. This is our entangled state. So that is equation 38, and say both particle positions x1 and x2 in the upper halves of their respective packets. The outcome of the measurement in particle 2 depends on what Alice chooses to do in the vicinity of particle 1. And so that again is showing the non-locality here. If Alice subjects particle 1 to the Stern-Gerlach based measurement, that measurement will have outcome spin up, and the conditional wave function of particle 2 will collapse to the state proportional to the spin down, and the subsequent measurement particle 2 spin will have the outcome spin down. On the other hand, if Alice removes the Stern-Gerlach device, the measurement in particle 2's z spin will instead have the outcome spin up. It is clear that the non-locality is a form of contextuality in which the part of the experimental context affecting the realized outcome of the experiment is remote. Although we have focused here on the concrete example in which the z components of the spins of both particles are perhaps measured, it should now be clear that and how the pilot wave theory accounts for the empirically observed correlations in the more general sort of case in which arbitrary components of these spin are measured. And so let's say that we don't have to have just the spin in the z direction. We can do this in multiple different orientations. And so we don't have to have it just be the z direction. So one of the particles will encounter its measuring device first. The outcome of the first measurement will be determined by the random initial position of the measured particle within its wave packet. The completion of this first measurement induces a collapse on the distant particle's conditional wave function. This in turn determines the statistics for a subsequent measurement on the distant particle. And so this again is just generalizing the thing that we're talking about, saying that we can do this for any orientation. That so much hangs on which measurement happens first, or more mathematically, that the conditional wave function of each particle is in the two-particle wave function evaluated at the actual current position of the other particle, no matter how distant, makes it clear that the non-locality of the pilot wave theory will be difficult to reconcile with relativity. This is, however, in principle no different from non-locality implied by the collapse postulate of quantum mechanics. And so he's saying this because a lot of times the non-locality of pilot wave theory is held up as one of its weaknesses, but this non-locality is something that's intrinsic in pretty much all interpretations of quantum mechanics. And so to hold this up as a weakness of pilot wave theory is being somewhat hypocritical. Indeed, the collapse of the pilot wave theory's conditional wave functions can and should be understood as a mathematically precise derivation of the usual textbook approach to measurement in a theory where imprecise notions like measurement play no fundamental role. And of course, the grossly non-local structure of the pilot wave theory and ordinary quantum mechanics turns out to be characteristic of any such theory, which reproduces the same quantum mechanical predictions as shown in Bell's other landmark paper, so the Bell's inequality. And so this collapse of the conditional wave function is something that kind of bothered me, and I looked through a lot of the literature on this, trying to find what is actually meant by the collapse of the conditional wave function, because what we see here in the paper, what I've put on here, is, like I said, almost verbatim from the paper that I got this from. And so it doesn't really say what is actually kind of meant by this collapse of the conditional wave function. And I had a hard time finding anything about it in any other papers as well. But what I did find is something that's called the empty wave. So empty waves and entanglement. And so this, what comes after this dark bar here, is all stuff that I have written. And so this does not come from the paper by Norson. And so this is my way of trying to think about or to interpret what is meant by the collapse of the conditional wave function. So these are my own thoughts here. And so don't attribute these to Norson or anybody else if these are actually incorrect. And so what I wrote here is, how is it the conditional wave function collapses in quantum entanglement? This gets into a prediction of pilot wave theory, namely empty waves. So in pilot wave theory, waves guide particles, but particles do not influence the behavior of waves. If they did, then the Schrodinger equation would not work, because we'd have to add some kind of other term in it to account for what the particle is doing to the wave. But we know that the Schrodinger equation does work. It does give us good predictions. And so pilot wave theory predicts that the particles do not influence the waves, only the waves influencing the particles. So the wave function psi can be a superposition of states, such as the spin up in the z and the spin down in the z, which is given by something that looks like this. So the particle follows the wave function. It is guided by the wave. That's kind of the foundational principle of pilot wave theory. So if the two entangled particles are in a superposition like this, so this is that non-factorizable wave function here, what we really mean is that the particles are being guided by a wave that is in a superposition of states. So remember, the particle itself is not in a superposition, but the wave can be described as a superposition of states. Thus, when particle 1 is measured and found to be, say, spin up, then particle 2 will be measured spin down, because it collapses into being guided by just this part of that wave function. So we have the psi 1 plus and psi 2 minus, which is what we see right here. However, no wave actually collapses. So remember, in the Bohmian mechanics, we don't actually have any wave function collapse, because that's one of the things that it is trying to avoid, is this collapse postulate. So what happens is that the particles instantaneously choose a component of the wave. So one of the terms in the linear combination. We can kind of see that here, where it's sort of like it's choosing this one. So when you measure particle 1 and it happens to be going up, then it's like it's saying that the particle 2 has to choose this part of the wave function here. So it has to choose one of the components of this wave function. And it does that instantaneously. This wave then ends up being empty, because the particle 2 is chosen to be part of this component of the wave. And so this component of the wave is empty. And so this is what I mean by Bohmian mechanics predicts that there would be empty waves. But this prediction of empty waves is even more interesting than this. And this has to do with the multiple worlds interpretation of quantum mechanics. but I won't go into this right now. I'll actually talk about this more in a future video. But if you are impatient and want to check out more stuff on the empty waves and what this might mean for sort of combining pilot wave theory with the multiple worlds interpretation of quantum mechanics, I do have some stuff in the further reading down here. And so this stuff here on empty waves, and especially this video here from PBS Spacetime, where it shows kind of the way that we could try to combine these two theories. Because to make a long story short, what it's essentially saying is that these empty waves are just the other worlds in the many worlds interpretation of quantum mechanics. And so, like I said, the Bohmian mechanics makes the prediction that there will be these empty waves, and the way I am trying to interpret the collapse of the conditional wave function is that the collapse is essentially not the wave itself collapsing, but the particle choosing which component of the wave to actually be guided by. And so that's, like I said, my interpretation here of what the collapse of the conditional wave function actually is. But anyway, that was what I wanted to talk about in this video. I'm only going to make one more video, or at least at the time of recording this, I only have one more planned on Bohmian mechanics, where I'm going to talk about perhaps some of the weaknesses of Bohmian mechanics and some of the places where it still doesn't really come up with all of the best predictions that we have, in particular when it comes to relativistic quantum field theory. But anyway, again, I've been saying this in the other videos. These videos do oftentimes take quite a bit of time and effort to make. If you are getting something out of these videos and you want to maybe make a small donation, I do have a Patreon campaign, which is linked to in the description down below. But I don't want to harp on that too much. I hope you found this video interesting, and I will see you in the next one.